Hi students. Today we will discuss about the analytical solution of the differential equation of law of radioactive decay process. Okay, so this is the differential equation which represents the law of you can say radioactive decay process. Okay, equation 1 here. uh, Here means capital N is a number of radioactive nuclei means the undecayed number of nuclei at any time t. At any time t. Okay, and lambda is a decay constant. Decay constant having units of say uh, units of let's say second inverse means 1 over means the units of 1 over time, and whose reciprocal means whose inverse, that is 1 over lambda, is the average lifetime is the average lifetime of radioactive nuclei. That is 1 over lambda is actually equal to tau average. Okay, last time we also discussed that how do we get the average lifetime. Okay, and here, and t is you can say independent variable. Okay, and no doubt if we say the n, that is a dependent variable, and again n is a dependent variable. Okay, and dn over dt itself, we already defined it, that this is rate of, you can say, decrease of radioactive nuclei with passive time. And this differential equation, because the differential equation has differential equation 1 has you can say only one independent variable, therefore equation 1 is a only differential equation. Okay, means only differential equation means in which the dependent variable only depends upon one independent variable. Okay, that means the dependent variable n is only depending upon the independent variable time t. So the solution of the ordinary differential equation, that is equation 1, that will be actually obtained to be the dependent variable n in terms of the independent variable, that is time t. Okay. Now because dn over dt is equal to minus lambda n is you can say differential equation, and other differential equations can be, you can say, solved in order to get the particular solutions in two ways. We can use either the initial conditions or the boundary conditions. So we can solve this problem in both ways. Okay, first of all, we will see that how do we solve this differential equation as an initial value problem. Okay, so first of all, we will solve it as an initial value problem. Okay, so that means solution as solution by taking dn over dt is equal to minus lambda n as an initial value problem, as an initial value problem. Okay, so this is the one way of solving this equation. Here the initial conditions are initial conditions are that at t equal to 0 n is equal to n naught, right? So we can apply this initial condition in order to get particular solution of the differential equation. For solving it means for solving the differential equation dn over dt, you know that we will shift capital N from the right side to the left side, and we will take the differential element dt on the right side. That is dn over dt, dn over n equals minus lambda t, right? Now we can integrate this equation dn over capital N is equal to minus lambda t on both sides. In integrating on both sides. Okay, means the left side will be integrated with respect to n, and the right side will be integrated with respect to time t. Okay, I'm sorry, this is dt. Okay, okay, so we integrate on, you can say, both sides. The left side is integrated with respect to the number of, you can say, with respect to the differential element dn, and the right side is indicated with respect to the differential element dt. Okay, this gives us, you know that this is the natural log of n, right? Natural log of n is equal to minus lambda t and plus some constant of integration, let's say c, or the arbitrary constant c. Now let's say this is equation number 2. Here equation 2 gives us you can say general solution of equation 2, where equation 2 represents represents a general solution of dn over dt equals minus lambda n. Okay, so this is equation 2 is a general solution of the differential equation. This is called as the general solution because here the constant of integration is not known. Okay, if we want to find the value of the constant of integration, we can apply the initial conditions. Okay, the initial condition which is already given here, this one. Okay, so applying initial condition, initial condition on equation 2, that gives means when we put t equal to 0, we will get means put t equals 0 and n to be equal to n naught. This is the initial condition we want to put here. Okay, right. Okay, so writing equation 2 again, that is you can say natural log of n equals you can say minus lambda t plus c, right? So this is equation 2. So after initial conditions, after initial condition is you can say used in equation 2, we get that is natural log of n naught equals minus lambda 0 plus capital C. Okay, so this means capital C comes to be natural log of n naught. Okay, so putting this value of C in equation 2, putting the value of C in equation 2 gives what? That is natural log of n is equal to minus lambda t plus the natural log of n naught, right? Okay, so shifting this log of n naught on the left side, that gives us natural log of n minus natural log of n0 is equal to minus lambda t. So applying here the rule of the differences of the log of two values gives us log of n over n0 equals minus lambda t. Okay, so applying anti-natural logarithm on both sides, we get n is equal to n naught e to the power minus lambda t. This is, let's say, equation 3, right? Equation 3 is you can say here equation 3. This is equation 3 and it's equal to n naught e to the power minus lambda t. This is equation 3, right? So equation 3 is a particular solution of the differential equation. That means here equation 3 is a particular solution. You can say solution of dn by dt equals minus lambda n. That is the differential form of law of radioactive decay process. Okay, so this is the particular solution of this differential equation. Okay, so in this you can say step, in this stage actually we have solved this differential equation by taking this differential equation as an initial value problem. Okay, so this equation can also be solved by taking this differential equation as a boundary value problem. Okay, so we will do that. Okay, that is now we will do that. That how do we solve this differential equation as a boundary value problem? So let's see. Means the boundary conditions are, means the second way is, that is solving dn over dt equals minus lambda n as a boundary value problem, as a boundary value problem. Okay, this is the next thing we want to do. Okay, this is the next thing we want to do. Means we want to solve dn over dt is equal to minus lambda n by using you can say boundary conditions. Okay, let's do that. Okay, student, you must keep in mind that in both ways, whether we are using dn over dt is equal to minus lambda n as an initial value problem, or we are using it as a boundary value problem, in both situations, we must have the particular solution to be same. Okay, if you can say we are not changing, you can say the initial condition, right? And we are using the appropriate boundary conditions. Okay, let's do that. So uh, means here we can specify here the boundary conditions, right? Boundary conditions. One boundary condition is the same as the initial condition we have already used. Okay, that is at t equals 0, the value of n is equal to n naught, right? And the second boundary condition can be taken to be a general boundary condition. That is at, you can say, at any time t, at any time t, you can say the number of radioactive nuclei, just generally speaking, that is capital N. The number of, you can say, number of radioactive nuclei itself, means that is capital N, and itself is equal to N. We know that this capital N is equal to itself also. So this is a general boundary condition. Okay, so by using these two boundary conditions, we can get again a particular solution of the differential equation. Let's do that. It is now you can say integrating you can say dn over dt, dn over n is equal to minus lambda dt. Okay, and this as a definite integral, definite integral. Okay, because the definite integral means in which we know, you can say, the lower limit of integration and the upper limit of integration. Okay, so here you can see that in case of dn over n, on the left side we can use you can say the lower limit and the upper limit of integrations to be, let's say, starting value of n is n naught, and the finishing value or the upper limit of integration of this left side is capital N itself. Okay, and on the right side that is minus lambda, you can say dt. Here the starting time can be taken to be t naught, or let's say if t naught is taken to be 0, let's say, and the final time is taken to be time t. In that case, we can integrate through a definite integration style. Okay, so we get, look at, this gives us what? This gives us natural log of n equals, means the limit of integrations are n naught to n, right? And over here we have minus lambda t, and the limits of integration per time are 0 to t, right, itself. So in this case, by applying the limits of integration, we get, you can say, natural log of n itself minus natural log of n naught equals minus lambda. Inside will be, you can say, t minus 0. Okay. Okay, so by further processing, we can get it to be natural log of n over n naught, right, here, equals minus lambda t. Okay, so this gives us n is equal to n naught e to the power minus lambda t. This is equation 4. Okay, so by comparing the previous equation 3 and this equation 4, we can see that in both situations, whether we are using or we are solving the differential equation dn over dt equal to minus lambda t as an initial value problem, or we can solve this differential equation as a boundary value problem. In both situations, here we are getting the same particular solution. Okay, so this means whether uh, whether you solve a problem uh, as an initial value problem, as an initial value problem, initial value problem, or as a boundary value problem, you can get same solution. You can get same particular solution, same solution. Okay, that's all. So the solution provided by equation 3 and this equation 4 are the particular analytical solutions of the differential equation we were, you can say, solving. Thank you, students.